Okay, hi everyone. Please welcome Jeremy Gibbons. He's a professor of computing at the University of Oxford. He leads the Algebra of Programming research group and is co-editor-in-chief of the Journal of Functional Programming and formal chair of the IFIP Working Group 2.1 on Algorithmic Languages and Calculi, which designed Algol 68. His recent book, Algorithm Design with Haskell with Richard Bird, has just been published by Cambridge University Press, and you really ought to check it out. And he's also the author of a lot of fascinating functional pearls, and it feels like Jeremy could talk about anything and still make it fun and approachable. Today he will talk about how to design co-programs. So please welcome Jeremy Gibbons.
Great, thanks very much, Orlando. So yeah, welcome everybody to this great conference. It's great to have a big conference just about Haskell. Thank you to Ollie and everyone for organizing it. And although these are strange times, it's wonderful that we can have people from all around the world taking part. And it's a glorious day here in Oxford. I hope it's nice where you are. I have 45 minutes. I'm going to pause at 3 points in the middle of the talk and 1 point at the end, in case anyone has any questions about the material, to explore it a bit. Also, if there's anything that's unclear as I'm going, feel free to interrupt via Armando. So tell Armando and he'll interrupt me to ask for clarification. And then afterwards, there's chance for further discussion on Zoom. There's a Zoom discussion room, which I'll be in. But I've had to break into the department to deliver this talk, and I have to leave after an hour. So I can only be in the Zoom room until the next talk starts, and then I'll have to go as well. You can keep talking without me, of course. So we have when you're a beginning programmer, you have a problem. Somebody gives you a programming task to solve, and you have a blank editor window in front of you, and you're puzzled. Where does the program come from? Where do I start? How do I start filling in this blank window and make my program work? So a lesson that we teach, and a lesson that is very important for beginning programmers to learn, is a good place for starting is to analyze the structure of the input data that you're processing. So the structure of your program comes sometimes, often in fact, from the structure of the data that it's processing. So, for example, if you've got a program H whose input is a list, consumes a list, there's a picture of a linked list on the right-hand side of the slide. Then the advice says the function H, the structure of the function H should follow the structure of lists. So lists can be empty or non-empty, so there should be a case in H for empty lists and the case in H for non-empty lists. And for a non-empty list, the non-empty list has a head X and a tail X's, and so the X and X's are probably going to be used in the solution, so on the right-hand side of the second equation, the equation for non-empty lists. So that's a good start. You can already start writing part of your program if you know that it consumes a list. Lists are recursively structured. So in a non-empty list, X cons X's. X's is another list, and you're defining a function that works on lists. So another thing you could try is a recursive call. You can use H on X's as well. And beginning programmers might be a little bit suspicious of recursion when they first see it. It's not clear that this is well defined. You're defining H in terms of itself. Of course, we know that if the argument is reducing and gets to an endpoint like the empty list, it will always deliver you an answer eventually. But anyway, H of X's is well typed. X's is the right kind of thing to feed to H, so that's another thing you could try. And so the structure now says H of the empty list is something, you just have to work out what that is. For a non-empty list, you can use X, you can use X's, and you can use the result of a recursive call of H on X's. And in fact, often you only need the x and the h of x's, and you don't need x's, the bare x's itself. So this is an important message for beginning programmers, and it's one that's central to this very nice book, How to Design Programs, by Matthias Felleisen, Robbie Findler, Matthew Flatt, and Krishnamurthi. And of course, this book is the inspiration for my title, for the title of my talk. So the book is structured around what they call design recipes, which, if you like, design patterns for programs. There are names, and there are stories, and there are structures, skeletons, and advice on how to complete a recipe, complete a program using a particular recipe. And some of the design recipes, many of the design recipes are initiated by input structure. So one of the design recipes says if you have composite input, like a record, then the skeleton of your program, there's a design recipe for that, and the skeleton of the program says, well, the fields of the record, the components of your composite data structure, are probably going to be used in the program that has consumed that record. So you can start off by naming the components, and I'll show an example on the next slide. If your input data is mixed, a union type or a variant record, then like with lists, consider enumerating the alternatives. The input has to be one or the other, and so the program needs cases for one or the other. And if your input is inductive, like a list or a tree, then use structural recursion, as we've seen with functions over lists. So examples of those. Here's some composite data, an ordinary playing card, a regular playing card, which has a rank and a suit, like the rank could be queen and the suit could be hearts. And if you're wanting to do something with one of these cards, like turn it into a string, then name the components. R is the rank of the card, S is the suit of the card, and the solution is probably something to do with R and S. So you can start by writing that skeleton, the skeleton, and then you have to think about what the dot 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 should be. Which particular string do you want that might involve R and S? So that's all very straightforward. For mixed data, so here's now a regular playing card or a joker, and if you want to print one of these, then you need a case for regular playing cards, and we've just seen how that works, and a separate case for jokers. So you need to work out what string to give for jokers. But the point here is that you enumerate the alternatives. There are two of them, regular cards and jokers, and the program has a case for each. And for inductive data, use structural recursion. So one of my favorite examples of this is insertion sort, which is one of those instances where you don't need the bare x's. To insertion sort the empty list, of course, you get the empty list. And to insertion sort a non-empty list, a cons x, you need the sorted version x, and that's all you need. And in fact, what you do then is insert a into the sorted version of x. So the bottom of the slide is this function insert that does the work of one step. And you'll see that this one does need the full pattern for h, because sometimes it uses a recursive call on x, but sometimes it uses x without the recursive call. But I hope that's perfectly straightforward. You could define insertion sort without much difficulty. It's an example following the pattern. But this is only half the story. That's how to design programs, and I want to tell you how to design code programs, which is a dual kind of story. So at that point, I'm just going to check that everyone is on board. You can all hear me. Everything is clear. Armando, are there any questions?
All good so far, Jeremy.
Okay, good.
You feel free to, yeah.
So we had this table of program structures, input structures, and skeletons of programs that correspond to them. And the message, which is emphasized in the book, How to Design Programs, is that program structure follows data structure. But of course, we've got some of the data here, the input data, and we're missing the output data. The output data is also data. The output data also has structure, and the structure of that output data might also be helpful in coming up with your program. So the output might be composite data, it might be mixed data, it might be inductive data, and then the corresponding skeleton of the program might be determined by that instead. So for a composite output data, if you want to produce a record, then you're going to have to produce each of the fields of the record. So you're going to have one subprogram or function or clause or whatever for each of the fields of the record that you have to produce. If you're producing mixed data, then again, you enumerate the alternatives. In some cases, you produce one variant of the data, and in other cases, you produce a different variant of the data. And for inductive data, like lists and trees, you use structural, well, not structural recursion, but structural co-recursion. And I'll show you examples of these three. So here's some composite data, a date. A date has day, month, and year. And if I want to produce a date, for example, if I want to extract a date from a string, one skeleton program structure says, well, I've got to produce a date. It has to be a record. It has to have day, month, and year fields. And those values are, well, I don't know yet, but let's call them D, M, and Y, and have one subprogram for each component of the composite. One subcomponent for D, one for M, one for Y. They're each going to depend on S, of course, and I don't know yet which particular date I'm going to get out of a string. I'll have to do some work, but that's the skeleton of the program that determines where I can start. So that's something that you can try if you have a blank editor window and you need to produce a record. Here's some mixed output data. So this is division, which takes a pair of integers and produces their quotient rounded down. But of course it might fail because the divisor might be 0. So this is producing an optional result. It either produces just the quotient if the divisor is non-zero, and it says nothing if it produces nothing if the divisor is 0. So in Haskell, that's the maybe data type, and there are two constructors for it, nothing and just. And so the two alternatives for my program are to produce, sometimes it produces nothing, sometimes it produces just. So the advice, the skeleton, is to consider each of those alternatives separately. You can't, there's not much else you can do. You have to, if you're going to produce a maybe integer, and you are sometimes going to produce nothing and sometimes going to produce just, then basically you need two clauses. So this is a case analysis on the input, and it's also a case analysis on the output. So you might be wondering why I've called this structured on the output. It's a case analysis on the input, either the y is 0 or it's not. But it's a case analysis on the value of the input and not the structure of the input. So it's not using the structure of the integers, which might be the piano naturals with negative numbers, or it might be a pair of naturals representing the difference between them. I don't know and I don't care how integers are represented. I'm not using that representation. I'm doing some arithmetic on them instead. In contrast, the output data type is maybe, the output constructors are nothing and just, and they appear literally in the program. So the structure of this program is better explained as a case analysis on the output, nothing and just, than as a case analysis on any input structure. It's a case analysis on input value, it's not a case analysis on input structure. So if you're trying to emphasize the message that program structure comes from data structure, here you have to say the structure of this program comes from the output data structure, because that's the only data structure that appears in the program. So that's mixed data, and here's inductive output data. So here's a list again on the right-hand side, and a program that produces a list, program H, that produces a list. A list, as before, it has two variants. it's either empty or it's not, so there's going to be a clause for when the output is empty and a clause for when the output is not. And when the output is not empty, x cons x's, it's composite. You have to yield an x and an x's, so have a subprogram for x and a subprogram for x's. And that's the skeleton of your program. So if you're producing a list, one thing you can try, rather than trying to do case analysis on any input, is to do case analysis on the output. And again, the tail x's is another list, so that's typically given by a recursive call, just as we saw with structural recursion. So here, x is something to do with the input z, what is the head, and x's is a recursive call on some other seed. So I'm not constructing an arbitrary tail, I'm constructing a tail x's by computing a recursive call of h on some new seed z prime. So these are the questions you should ask yourself when defining a function that produces a list, in this case, by structural recursion. You have to say, when is the output going to be empty? Because that's when you produce the empty list. And when the output's not empty, where do I get its head from? So what is the head of the list? And from what seed do I grow the tail of the list? And then you get a nice structured program. Not all programs that produce lists have this nice structure at the bottom. They don't all have a direct recursive call to produce the tail. The ones that do are called unfolds. So sometimes you just have to live with this, this slightly less structured version. But often the program you want is in fact an unfold, especially when it's an introductory programming course and the programs you're writing are easy programs. And so this is a useful structure to bear in mind. So an example, another one of my favorite examples is sorting. Again, selection sorting this time. So selection sort is where you have a pile of unsorted stuff and you pick out the minimum one, that's the head of the list, and then you pick out the next minimum one, that's the next element of the result, and so on. So selection sort says, when is the output list of sorting empty? Only when the input list is empty. So here we have a case analysis, well, the decision that says when the output list is empty, it's if the input list is empty. Otherwise, what's the head of the list? It's the minimum. And from what do I get the tail of the list? So what do I have to sort to get the tail of the list? And what you have to sort to get the tail of the list is the original list minus the thing you just plucked out of it, minus singleton A. So this double backslash is Haskell's function for removing the elements of one list from another. So that's another tool in your toolbox. You can define functions by structural recursion, and that's all the advice you get in the How to Design Programs book, really. But you can also define functions by structural co-recursion. And my point is that the How to Design Programs book should also be How to Design Co-Programs and should also have this structure, this design recipe in it. Of course, if you have more tools in your toolbox, then you've got more options, more ways you can solve problems, more programs you can write. Some things look difficult from one angle and easy from a different angle, and a different tool can show you that different angle. So here's an example. I want to zip together two lists. So I've got a list of alphas and a list of betas, and that's going to make a list of alpha-beta pairs. The example on the right shows the alphas and betas are both numbers here. So I've got a list 1, 2, 3, I've got a list 4, 5, and I want to make a list of pairs. Those lists are of different lengths. So let's, for simplicity, say zip stops when the shorter list runs out. So this produces the list of pairs 1, 4, 2, 5, and then stops because there's nothing to pair up with the 3. And following the How to Design Programs recipe, you've got structured input lists. In fact, you've got 2 of them, and you have to do case analysis. And already the fact that you've got 2 of them gives you a a head-scratching moment. Which input do you do case analysis on? So here I've done case analysis on the left-hand input. So if x's is null, then, so there's a case for x's being the empty list, and then the remaining cases are for x's being a non-empty list. I could have done that by pattern matching. Maybe I should have done that by pattern matching. When x's is null, then it doesn't matter what y's is, the result is empty because the left-hand list has run out. Otherwise, what list do I produce? Well, now I need to do a case analysis on the right-hand list as well, because if the left-hand list is non-empty, I still might get some results or I might not, depending on whether the right-hand list is empty. So I do a case analysis on the left-hand list and then a case analysis on the right-hand list. And only if they're both non-empty do I produce something. It's the head of both lists is the first pair, and then I zip the tail of the two lists. So that's case analysis on the first input. Case analysis on the second input wouldn't give a very different program. It would just be a test against null y's first and then a test against null x's. If you do case analysis on both lists at once, well, each list can be empty or not, and so that gives you 4 cases. So that doesn't seem like an improvement. I've turned a 3-case program into a 4-case program. That seems more complicated, so it doesn't look there like the design recipe for programs is helping. And of course, I picked this example because the design recipe for co-programs is more helpful in this particular case. It in fact takes a 3-way analysis into a 2-way analysis, which is clearly better. So to zip 2 lists x's and y's, when is the result empty? It's empty if either input list is empty. If either's exhausted, then you can't produce any pairs. Otherwise, they're both non-empty, and so it's safe to call head and tail on both of them. So this is zip with program structure following the structure of the output list. There's a case for the empty output list, and there's a second case for the cons, the non-empty output list, and there are only those 2 cases. So this is a much neater program for zip, and when I teach functional programming, I teach the programs pattern. I teach case analysis on the input and show people zip, and they're happy writing 4 cases for zip. And if they're clever, they might come up with 3 cases for zip. And basically what you have to do is rearrange the branches, but they don't see it as a case analysis on the output. And I think this is a missed lesson. So let me pause there. That's co-programs, which are structured on the structure of the output. Armando, any questions yet? You seem to be muted to me, Armando. Okay, I'll take that as a no. Let me move on. So the book, How to Design Programs, doesn't stop with structural recursion. That's early in the book, and there's lots more. And there are patterns for design recipes for various kinds of program structures, and they write games and all sorts of interesting things. So it's quite a long book for quite a long course. But most of the patterns are not about program structure. They're not, or at least they're not about, I take that back, they're all about program structure, but they're not about program structure arising from data structure. Most of them are not. There's one more that is. They present it much later in the book, a much more advanced strategy, and it's called generative recursion. So structural recursion, you do a recursive call on a subproblem. So to insert sort a list, you insert sort the tail of the list, and that subproblem is just obtained by projecting out of the input data. So to get the tail of the list, you just have to project the x's out of x cons x's. It's a very trivial computation to produce a subproblem on which you do a recursive call. Generative recursion is where you do something more significant than just projection to extract the data for a recursive call. Some real computation is involved in finding the subproblems on which you do that recursive call. So the skeleton for generative recursion incorporates a test for when the problem is trivial. When the problem is trivial, you don't divide it into subproblems, you just solve it directly. And when the problem is non-trivial, then you have to split it into subproblems, doing some computation somehow. Recursively, you solve each of the subproblems, and then you assemble those, the results of those subproblems into the overall result. So there's a picture on the right-hand side of a non-trivial input, which is split into subproblems, smaller problems, and they're split further into subproblems. At some point, these become trivial, and you can directly turn them into solutions. And then you have to assemble smaller solutions into larger solutions. So solutions to smaller problems into solutions to larger problems. And you keep doing this until you've solved the whole problem. So obviously, this is a divide and conquer kind of picture that I've drawn. Generative recursion is most interesting when it's divide and conquer, but that's not the only instance. While loops are a special case where when you split a problem, you only produce one subproblem. But moreover, once you've solved the subproblem, there's nothing more to do to solve the problem. If there were something more, you'd need a stack in order to store all the things you had to do, and you couldn't implement it as a loop anymore. It would have to be a recursion, or somehow you'd have to implement the stack yourself. But in the case where there's only one subproblem and no reassembly required, basically what you've got is a while loop. So here's a program loop. When x is trivial, you solve it trivially, and otherwise you do one step on x and then continue the loop on that stepped value. So that's an instance of generative recursion, because the computation that yields the subproblem is more than just a projection. But as I said, the general case is divide and conquer, and the motivating example in how to design programs is another one of my favorite programs, Quicksort, which was defined by Tony Hall, actually before he came to Oxford, so before he was my boss. He was in Belfast at the time, but nevertheless, I'm going to claim this as an Oxford treasure. And this is the slow version of Quicksort. It's not the quick. It doesn't do stuff in place, and it has space leaks and quadratic appends and all sorts of horrible things. But it's a simple program structure, and it's a fine program structure for a beginning programming course. And it's a perfectly good programming structure to have in the How to Design Programs book. So how does this work? The sorting is trivial when the input is empty, and in that case, to trivially sort, you just produce the empty list. And sorting is non-empty non-trivial when you have a non-empty input. And in that case, what Quicksort does is partitions the input using, in this case, it uses the first element of the list as a pivot, and it splits the list X into the things Y that are less than or equal to the pivot and the things Z that are greater than the pivot. So it uses A as a pivot, and then you have the little elements to one side and the big elements to the other side. And they're just a pile on one side and a pile on the other side. And so, of course, you have to sort them recursively. So you quicksort the little things, you quicksort the big things. And now, because of the pivoting, the partitioning, you can just append them together in this order, because these are all little things. They're all less than or equal to A, and these are all big things. They're greater than A. And moreover, these things are in order and these things are in order now because we've sorted them. So this whole thing is sorted. So that's generative recursion. It splits the problem into two subproblems, Y and Z, when it's non-trivial, does a recursive call on each of them, and then assembles the results using append. So the nice thing about quicksort, one of the nice things about quicksort is that you can split it up into 2 phases, and I think it's very enlightening to do so. This program for quicksort is short, but it's also quite dense, and there's a lot going on in those few lines. And perhaps it's easier to see what's going on if you make it less dense, if you write a longer program that makes explicit more of the structure in the program. So really, quicksort is tree structured, and you can make that explicit by factoring quicksort into 2 phases, a build phase followed by a flatten phase. And build grows a tree from the input list, and flattens a tree back to the output list. So build just does the partitioning that we've seen before into little things and big things, but rather than appending, it just records those things. So you split the list in 2, and then split it in 2 again, and keep going until you get down to, pivoting with nothing left. Then you get empty trees. So that grows a tree, and if you do it with 31415, which has been my running example, it turns out that you get this tree. You picked 3 as the pivot, and then you make a tree out of the little things and a tree out of the big things. And then all you have to do is flatten that tree. It's a binary search tree. It's in order from left to right. So when you flatten it, you get a list that's in order from left to right. So, of course, you can see these list comprehensions are part of the quicksort program, and these appends are part of the quicksort program. I've teased the quicksort program apart into 2 parts. But now I can look at the 2 parts independently. And flattening is something that by the time students get to quicksort, they've probably already written something about trees. And they've already written this program. It's just structural recursion over trees. There's a case for the empty tree, and there's a case for non-empty trees. And in the non-empty case, you use the root, and you make recursive calls on the 2 children. Build consumes a list. So there's a case for the empty lists, and there's a case for non-empty lists. But the structure of the program is not determined by the structure of those lists. Because you don't have a recursive call build on X. Instead, build has a case for the empty tree and a case for non-empty trees, and in the non-empty tree case, recursive calls on other lists that generate other trees. So yes, it uses lists, and yes, there's a case analysis for empty and non-empty lists, but no, the structure is a mess when you look at it from a list point of view from that point onwards. So lists do not explain the structure of build. Trees explain the structure of build. Build is obviously tree structured, and flatten is obviously tree structured rather than list structured. So you need to see that. And the thing that makes generative recursion more advanced and more sophisticated from the how to design programs point of view is that the real structure, the real thing that's going on is about trees, and that's nowhere in your problem statement. You were sorting, this was something from lists to lists. Where did the trees come from? Well, that's a creative step, and there is no magic answer to where the creative steps come from. So some thought, some creativity, some insight is required. So it is a more advanced pattern design recipe. But it's very useful, I think, to be able to tease it apart into 2 components, be able to talk separately about the 2 components. And of course, this works. This is not something that's special about quicksort. It's true for all divide and conquer programs. Anything that looks like this is, you can even see it here, growing a tree somehow and then processing that tree. Of course, you might not want the whole tree to be in existence at once. And with quicksort, you don't have the whole tree in existence at once. And indeed, in Haskell, with lazy functional programming, you don't get the whole tree at once. But But in general, you can talk about deforestation. You can talk about eliminating the intermediate tree. Build grows a tree, which Flatten immediately takes apart again. And you can fuse these two phases of the quicksort. And of course, what you end up with is the one that doesn't have any trees in it, the one we started with. So there's a whole story you can tell about fancy programs arising out of optimizations of simple programs. That optimization is a useful thing to discuss because you might want to use the same optimization for your other simple programs to get fancy programs out of them. And that opportunity for discussion is all lost if you don't talk about structural co-recursion. So we should talk about structural co-recursion. The book, How to Design Programs, apologizes about generative recursion. So it says it's an ad hoc activity. You can think of it more like inventing an algorithm rather than designing one. Inventing because somehow you have to come up with this tree structure that wasn't there in the problem description. It requires a new insight and a eureka. And I think they're too defeatist, too dismissive. New complex algorithms, they say, often developed by mathematicians and mathematical computer scientists, but programmers like you know you can't be expected to have such algorithmic insights. You just have to wait for the clever people to invent them, and then you should be their programming slaves and implement them for them. You should communicate with the scientists who are the ones who invent the algorithms. I think that's defeatist. I agree that most programmers don't design new algorithms, but I think it's we're selling our students short if we don't tell them where these things come from when it's fairly obvious how the bits fit together. Even if there's still a creative idea, you just need to say that's the creative idea, everything else follows from that. So I don't think generative recursion is an ad hoc activity at all. I think it's a very structured activity. It just depends on different structure. Intermediate structure now, not input structure or output structure, but that intermediate structure is the output structure of the input phase and the input structure of the output phase. It's where the two phases meet. So this separation of concerns is, of course, really important. It's what computer science is all about in some sense. It's what science is all about in some sense. Here we're separating the dividing concern from the recombining, the reassembling concern. Separating means you can study the two parts separately, of course, and then you can put them together in different ways. So the divide and conquer thing is called a hylomorphism in the lingo. An unfold to grow a tree and then a fold to consume the tree. And you can talk about deforestation, and deforestation is something that comes up all over the place. That's a common trick that maybe is not needed in the first programming course, but is something that computer scientists and programmers should know. That's kind of the obvious way of putting together the co-recursion to grow a tree and the recursion to consume the tree. But you can put the components together the other way around. You can have a recursion to consume some input followed by a co-recursion to generate some output. And that turns out to be a useful pattern as well. It's, you can use it for change of representation. So the input might be a list of digits in one base, and you have to turn it into another base. So that input is a list of digits, you consume it to work out what value is being represented, and then you generate a new list of digits in a different base from the new value. And I've used that several times, in fact. I gave it a name, metamorphisms, because they change representation. You can use it for changing fractions from one base, for digit sequences in one base to digit sequences in another base. More interestingly, you can have funny bases in which transcendental numbers like pi have regular representations, repeating representations. So there's a very nice sequence for pi, which is a number in a funny base where the radix changes from digit to digit. And computing the digits of pi in base 10 is a change of representation, a change of base from this funny base to decimal. And the story is one of these metamorphisms. You can also think of data compression algorithms as changing a message in a text base to a message in a bytes base. So these are ASCII characters and these are bytes, and you compress them as you go. And the arithmetic coding is a nice example of a change of representation. That's another one of these metamorphisms. And you can't have that discovery if you don't have co-recursion to complement your recursion. Here's another thing that you might want to explore once you know about co-recursion. So here's another sorting algorithm, merge sort. What merge sort does is it just splits the list up into parts without doing any comparison. It doesn't do the partitioning like quicksort does. It just halves and halves and halves again till you get down to singletons. And then it merges them all back together. So it's another tree growing thing. And it's in two phases, like quicksort, a dividing phase that builds a tree and a consuming phase that consumes the tree. And you can write merge sort in this way. But if you do, it's a bit clunky because you have to have these two merge calls in the flattening case, in the merge all program. Why is that? The reason why is because it's not really the right structure of tree for this problem. Really, you want trees that have no internal labels because you just split a list in half, and you don't want to have the internal label. And so, in fact, you have a different structure of trees, one where the labels are at the leaves rather than at the nodes, the internal nodes. And I think this is a nice learning opportunity because we've got those trees lying around, let's use them for merge sort. You get a program, oh, it's a bit clunky. What do we do? Well, program structure is determined by data structure. If we change the data structure, what happens? You can change the data structure from these trees to different trees. And I'll skip the details, but they're in my blog post about this and also a paper I've submitted about this, which hopefully will appear soon. If you change the tree structure, you get a different tree structure, of course. So then you get a different program structure because data structure determines program structure. And you can pick the tree structure to make a nice program structure. So I think going through that whole exercise is a good learning opportunity for how program structure determines, data structure determines program structure. So pause again. Are there any questions at this point? Armando, can you hear me?
Hey,
yes.
Jeremy, last time I was having trouble with Zoom. There was a clarification question which I couldn't relate to you, so I apologize for that. I hope the person in question asks it in the Q&A room because now I think it's a bit too late for that. So so far, besides that one question, all is good. So
Okay,
I think we can continue.
Well, nearly done. Just a few final points. I've used Haskell as a notation in this talk, of course, because this is a Haskell conference. And anyway, of course, because Haskell's my favorite language. I did give a version of this talk for a 60th birthday symposium for Matthias Felleisen, who's not a Haskell fan, who's a Racket fan. And of course, the How to Design Programs book uses Racket. And I made no apologies then for using Haskell as my notation. We all know Haskell's much nicer. But you'll note that I have not used Haskell for its laziness. None of the programs I've shown use laziness in any essential way. You get automatic deforestation of the tree-based quicksort with laziness. And if you don't have laziness, then you don't get that. You really build a whole tree and then collapse it. But the programs still work. And for a beginning programming course, this story is fine. The story about corecursion is fine. It works perfectly fine in eager languages too, like Racket or Scala or Python or F# or whatever you want to use. If you don't have laziness, you need to make sure that your generating phases, your corecursions, terminate, because otherwise you'll never get around to the consuming phase. So you need a termination argument. You need to know when you're growing a tree, you don't grow an infinite tree. It will eventually stop. But that's, you need that anyway in all sorts of other examples in a programming course that uses an eager language. And in fact, in most programming courses that use lazy languages as well. So generative recursion, when you're dividing a problem into subproblems, you need to make sure that you'll eventually get to the trivial problems. Loops, if you're going and going and going until you get to the trivial case at the end, you need to make sure that you get to the trivial case at the end. Those termination arguments are no different for structural co-recursion than they are for the other cases that have to be discussed. So I have to say that maths is a bit prettier if you admit infinite data. Everything's more naturally dual, but that's not something that is relevant for a first programming course. I should say that I'm not the first to make these points. Norman Ramsey had a very nice paper at ICFP in 2014, an experience report on teaching from the How to Design Programs book. And in his conclusions, he says, you could design a functions template around the result type rather than the input type. If and when he teaches it again, he's going to place greater emphasis on this. And for example, on test coverage as well, good advice for test coverage is to provide examples to make sure every choice of input is represented, but also provide test cases to show every choice of output is represented, to make sure that you cover each possible branch of output. And this is especially valuable for functions returning Booleans. You might define a predicate that accidentally returns true everywhere. And to close, the ideas, in fact, are not new with me. They're really old. So there's this quote from Tony Hoare in 1972. There are certain close analogies between the methods used for structuring data and the methods used for structuring a program that processes that data. So that's in Tony Hoare's Notes on Data Structuring, which is a great paper from 1972. It's the thing that introduced pointer structures into languages like Haskell. And there are also nice quotes by Fred Brooks and Eric Raymond about data structure being the thing that explains your program better. In fact, How to Design Programs, the book, credits this approach called Jackson Structured Programming by Michael Jackson, a different Michael Jackson, from 1975, saying, I mean, with the argument that program structure is determined by data structure. But in that book, Michael Jackson writes, the structure of a program must be based on the structures of all the data it processes. So not just the input data, also the output data. And the point about Jackson structured programming is about reconciling the kind of data that was common in 1975, which was payrolls with stacks of punch cards. And they were structured one way on the input, and the point of a processing phase is to structure them differently on the output. And of course, you have to take both of those structures into account to write the program. So there's history there, and we should not forget that history. So my conclusion is that program structure follows data structure, not just the input structure, also the output structure. You need to pay attention to both. When the data is recursive, the programs are often recursive, but you should be aware of the possibility for structural co-recursion as well as for structural recursion. Those are separate tools, and if you have different tools, you can put them together, recombine them in different ways. And I thought tangrams were a nice example of that. You've got all these triangles and one square, and you can put them together into many different forms. But you need to have all the different pieces. So at that point, I'll stop, and I think we can leave this and move to the Zoom room now.